back to the CompTIA Network Plus course. Routing basics. Once you create an internetwork by connecting a wide Once you create an internetwork by connecting your wide area networks WANs, local area networks LANs to a router, you need to configure logical network addresses such as IP addresses to all hosts on the internetwork so that they can communicate via routers across the internetwork. In IT, routing essentially refers to the process of taking a packet from one device and sending it through the network to another device on a different network. Routers don't really care about hosts. They care only about networks and the best path to each network. The logical network address of the destination host is used to get packets to a network through a routed network, and then the hardware address of the host is used to deliver the packet from a router to the correct destination host. If your network has no routers, then it should be apparent at that, well, you are not routing. But if you do have them, then there's to then okay. But if you don't have them, they're there to route traffic to all the networks in your internetwork to be capable of routing packets. A router must know at least the following information: destination network address, neighbor routers from which it can learn about remote networks, possible routes to all remote networks, the best route to each remote network, how to maintain and verify routing information. The router learns about remote networks from neighbor routers or from an administrator. The router then builds a routing table, a map of the internetwork that describes how to find the remote networks. If a network is directly connected, then the router already knows how to get to it. If a network isn't directly connected to the router must use one of two ways to learn how to get to it. One way is called static routing, which can be a ton of work because it requires someone to hand type all network locations into the routing table. The other way is a dynamic routing. In dynamic routing, a protocol on one router communicates with the same protocol running on neighbor routers. The routers then update each other about all other networks that they know about and place this information in the routing table. If a change occurs in the network, the dynamic routing protocols automatically inform all routers about the event. If static routing is used, the administrator is responsible for updating all changes by hand into all routers. Understandably, in a large network, it's, a, it's common to find that a combination of both dynamic and static routing is being used. Before we jump into the IP routing process, let's take a look at a simple example that demonstrates how a router uses a routing table to route packets out of an interface. We're going into more detailed study of this process in a minute. So here we are looking at a figure 9.1, a simple routing example. Looking at figure 9.1, can you figure out which interface lab A will use to forward an IP datagram to a host with an address of 10.10.10.10? By using the Cisco command show IP route, we can see the routing table map of the internetwork the router lab A will use to make all forwarding decisions. Router A hash, show IP route, output cut, gateway of last resort is not set, C.10 10.10.10.0/24 is directly connected to fast Ethernet 0 /0. C10.10.20.0/24 is directly connected fast Ethernet 0/1. C10.10.30.0/24 is directly connected to fast Ethernet 0/2. C10.10.40.024 is directly connected to serial 0/0. The C in the routing table output means that networks listed are directly connected, and until we add a routing protocol, something like RIP, EIGRP, and so onto the routers in our internetwork or use static routes, we'll have directly connected networks in our routing table. So let's get back to the original question. By looking at the figure and the output of the routing table, can you tell what lab A will do with a received packet that a destination address of 10.10.10.10? If you answered, the router will packet switch the packet to interface fast Ethernet 0.0, and this interface will this frame the packet and send it out on the network segment. You're right. Just because we can, let's look at a different example based on the output of the next routing table. Which interface will a packet with a destination address of 10.10.10.14 be forwarded to? Router A hash chip route output cut gateway of last resort is not set. C 10.10.10.16/28 is directly connected to fast Ethernet 0/0. C 10.10.10.8/29 is directly connected fast Ethernet 0/1. C 10.10.10.4/30 is directly connected fast Ethernet 10.02. C 10.10.10.0/30 is directly connected to serial 0.0. First, you can see that the network is subnetted and that each interface has a different network mask. And I have to tell you, you positively can't answer this question if you can't subnet. No way. Here's the answer. 10.10.10.14 would be in a host in the 10.10.8/29 subnet connected to fast Ethernet 0/1 interface. The IP routing process. The IP routing process is actually pretty simple, and it doesn't change regardless of the size of your network. I'm going to use figure 9.2 to give you a picture of this step-by-step process. The question I'm asking in this: what happens when host A wants to communicate with host B on a different network? I'll go through how to answer that question by breaking down the process with headings to make it easier to understand. First, check out figure 9.2. Suppose that a user on host A pings host B's IP address. Routing doesn't get any simpler than this, but it still involves a lot of steps. A packet is created on the host. Internet Control Method Protocol (ICMP) creates an echo request payload, which is just the alphabet in the data field. ICMP hands that payload to IP, which then creates a packet. At a minimum, this packet contains an IP source address, an IP destination address, and protocol field with 01H. Remember that Cisco likes to use 0x in front of hex characters, so this could look like 0 dot 0, okay, 0x01. All of that tells the receiving host whom it should hand the payload to when the destination is reached. In this example, it's ICMP. Packet is forwarded. 3. After the packet is created, IP determines whether the destination IP address is on the local network or on the remote one. Because IP has discovered that this is a remote request, the packet needs to be sent to the default gateway so the packet can be routed to the correct remote network. The registry in Windows is parsed to find the configured default gateway. The default gateway of host 172.16.10.2 host A is configured to 172.16.10.1. For this packet to be sent to the default gateway, hardware address of the router's interface Ethernet 0 configured with the IP address of 172.16.10.1 must be known. Why? So the packet can be handed down to the data link layer, framed and sent to the router's interface that's connected to the 172.16.10.0 network. Because hosts only communicate via hardware addresses on the local LAN, it's important to recognize that for host A communicate with host B, it has to send packets to the media access control address of the default gateway on the local network. The Address Resolution Protocol ARP cache of the host is checked to see whether the IP address of the default gateway has already been resolved to a hardware address. If it has, the packet is then free to be handed to the data link layer for framing. The hardware destination address is also handed down with that packet. To view the ARP cache on your host, use the following command: c colon backslash ARP minus A interface 172.16.10.2 0x3 internet address physical address type 172.16.10.1 00 15 05 06 31 BO dynamic. If the hardware address isn't already in the ARP cache of the host, an ARP broadcast is sent out onto the local network to search for the hardware address of 172.16.10.1. The router responds to that request and provides the hardware address of Ethernet 0, and the host caches this address. After the packet and destination hardware address have been handed to the data link layer, the LAN driver is used to provide media access via the type of LAN being used. In this example, it's Ethernet. A frame is then generated encapsulating the packet with control information. Within that frame are the hardware, destination, and source address, plus, in this case, an ether type field that describes the network layer protocol that handed the packet to the data link layer. In this instance, IP at the end of the frame is something called a frame check sequence FCS field that houses the result of the cyclic redundancy check CRC. The frame would look something like what I've detailed in figure 9.3. It contains host A's hardware MAC address and the hardware destination address of the default gateway. It does not include the remote host's MAC address. Figure 9.3, frame used from host A to the lab A answer when host B is pinged. Destination MAC address, routers E0 MAC address, source MAC address, host A MAC address, ether type field, packet FCS CRC. When a frame is completed, it's handed down to the physical layer to be placed on the physical medium one bit at a time. In this example, the physical medium is twisted pair wire. The router receives the packet. Every device within the collision domain receives these bits and builds the frame. They each run a CRC and check the answer in the FCS field. If the answers don't match, the frame is discarded, but if the CRC matches, then the hardware destination address is checked to see if it matches to, in this example, it's the router's interface Ethernet 0. If it matches, then the ether type field is checked to find the protocol used at the network layer. Packet is pulled from the frame and what is left to the frame is discarded. The packet is then handed down to the protocol listed in the ether type field. It's given an IP. The router routes the packet. IP receives the packet, checks the destination address. Because the packet's destination address doesn't match any of the addresses configured on the receiving router's interface, the router will look up the destination IP network address in its routing table. The routing table must have an entry for the network 172.16.20.0 or the packet will be discarded. Immediately an ICMP message will be sent back to the originating device with a destination unreachable message. If the router does find an entry for the destination network in its table, the packet is switched to the exit interface, in this example interface Ethernet 1. The following output displays the lab A router's routing table. The C means directly connected. No routing protocols are needed in this network because all the networks, all two of them, are directly connected. Lab A/ship route code : C connected S static IG RP or RIPM mobile M BGP D EIGRP EX EIGRP external O OSPF IA OSPF inter area N1 OSPF and SSA external type 1 N2 OSPF and SSA external. Type 2 E1 OSF external, Type 1 E2 OSF external, Type 2 EEGP ISISL1 ISIS level 1 level 1 L2 ISIS level 2 IA ISIS inter area candidate default U per user static route OODRP periodic download static route gateway of last resort is not set. 172.16.0.0/24 is subnetted to subnets. C172.16.10.0 is directly connected Ethernet 0. C172.1620.0 is directly connected to Ethernet 1. The router packet switches the packet to Ethernet 1 buffer. Now that the packet is in the Ethernet 1 buffer, IP needs to know the hardware address of the destination host and first checks the ARP cache. If the hardware address of host B has already been resolved and is in the router's ARP cache, then the packet and the hardware addresses are handed down to the data link layer to be framed. Let's take a look at the ARP cache on the Lab 1A router by using the show IPARP command. Lab A/ship ARP protocol address age min hardware ADDR type interface. Internet 172.1620.1 00D0.58.AD.05F4 ARPA Ethernet 1. Internet 172.16.20.20.9492.A5DD ARPA Ethernet 1. Internet 172.16.10.1 /005 0015.05.0506.31BO ARPA Ethernet 0. Internet 172.16.10.212.0.030.9492.A4AC ARPA Ethernet 0. The dash colon means that this is the physical interface on the router. From this output we can see that the router knows the 172.16.10.2 host A and 172.1620 host A hardware address. Cisco routers will keep an entry in the ARP table for 4 hours, but if the hardware address hasn't already been resolved, the router then sends the ARP request out E1 looking for the hardware address of 172.16.2.0. Host B responds with its hardware address, and the packet and hardware destination address are both sent on to the data link layer for framing. The data link layer creates a frame with a destination, source and hardware address, ether type field and the FCS field at the end. The frame is handed to the physical layer to be sent out on the physical medium 1 bit at a time. Finally, the host receives the packets. Host B receives the frame and immediately runs a CRC. If the result matches what's in the FCS field, the hardware destination address is then checked. If the host finds match, the ether type field is then checked to determine the protocol and the packet to be handed to at the network layer in this example. So I'm going to leave it here at today for this video. If you liked, consider like, sharing and subscribing. Thank you very much.